Okay, so this is a problem about a steady state temperature distribution inside of a wall. We have the thermal conductivity, we have the thickness of the wall, we also have the profile of the temperature distribution with the numbers plugged in there. We're supposed to find the heat generation rate, which is Q dot in the wall, and then determine the heat fluxes at the two faces of the wall. What manner are these heat fluxes related to heat rate, so on and so forth. We're mainly going to focus on A, and then I'll calculate B and talk about it a little bit. So, in order to do this problem, you have to start with the heat equation. So the heat equation, just like this. What you have is a partial with respect to x of k of delta t over delta x plus q naught is equal to rho cp delta t or partial t with respect to t. Okay, so and I'm also going to draw a picture. So this is what we're going to start with. You only have heat generation moving in the x direction. So if you were to draw this wall, what you would see is the T1 and all that stuff on this side, and then you have T going through like this, and this is the temperature. So it starts higher over here, then it gets lower based on the equation. T of R, or no, T, not T of R, but T of degree C. There we go. Alrighty. Okay, and then the T of C, T of degree C is equal to, that's going to be equal to 200 plus negative 2000 x squared. So that's going to be your TC as you go into this. Alright, so working with this equation, we know that it's a steady state problem. So you know that all of this is automatically going to go to 0. But we do have heat generation, and we're trying to find that. So we're going to use that and this part right here. So going ahead and taking this part onto the other side, we've got the heat generation is equal to K, and then I'm going to group the partials. So partial squared of T over partial of X squared. And that's a negative K because I subtracted it from this side to take it over there to 0. So here is our equation. That's pretty much all we have to do. Now what we're going to do is go ahead and take the double partial of this equation right here. So which is equal to negative K partial with respect to X. The derivative of that, because I'm going to take out one partial and just do one derivative at a time. So that's going to end up as negative 4,123,000 x, just like that. Excuse me. Right, just like that. And then moving on one more, if we take the derivative of this yet again, we're going to end up with negative K. Take the derivative of this, and you end up with negative 4,000. Just like that. Q dot. So then all you have to do is go ahead and sub in K. Q dot is equal to negative K is equal to 50 watts per meter Kelvin minus 4,000. 1, 2, 3 degrees C per meter squared. And if you solve that out, you get Q naught equal to 2.0 times 10 to the 5th watts per meter cubed. That's how you find the heat generation rate. So you just start with the heat equation, you set it up and make all the assumptions and eliminate anything you don't need. We only have heat transfer in X, so the other two values, Y and Z, can be eliminated. And then you solve for Q naught or Q dot, and then go through, do the derivatives, and everything just works out. It's actually pretty easy. Now to determine the heat fluxes, the heat flux, Q double dot, is going to be equal to negative K of dt dx. So again, this is pretty easy. This is actually a continuation of this same problem up here, because if you've got the heat generation, if you want the heat generation through an area, you go ahead and eliminate a derivative and do a little magic here and there and yonder. You actually have this introduced in your book, so I'm not going to go into the magic of it, but this is what the equation is. So if we sub in the temperature equation again, this time I'm going to do it in variable form just to mix it up. Negative K d over, can't see it, okay, a plus bx squared all over dx. So the derivative with respect to x, and you end up with negative k of 2bx equal to 2 double dot, just like that. So with it at these two walls, you have this spot at x equal to 0 and x equal to L. And this is L is actually equal to 0.05 meters. So in order to go ahead and print that out, you'll find out that Q0, Q double dot of 0 is equal to 0, just because there hasn't been any volume yet to generate that. You're over here at the side of the wall, there's no volume yet to create that heat generation. But then at Q of 0.05, you've got negative 30, or no, not negative 50, 30, negative 50. I'm not gonna put in the units just because to save time. 2 times B is negative 2,000, times x, which is 0.05. If you calculate that, you'll end up with 10,000 watts per meter squared. So, yes, that's right. Because the negatives cancel and you end up with positive value. Q double dot, right there, right there. So, if you want the relation of that, if you want the complete relation of how the energy works, what you can do is use the energy balance equation. So, E in is equal to E out. And you find that, let me make sure I'm doing this correctly. Double check my work. You have Q double dot in the x direction of 0 minus Q double dot in the x direction of L plus Q dot of L is equal to 0. So the heat generation and the heat fluxes all have to add up to 0. And if you want to, this is actually a negative, because you've got this heat generation minus the heat flux, which is the heat that's moving away from the generated area. So that's how that works. And then solving for Q dot, you end up with Q dot equal to negative Q x of 0 plus Q double dot x of L all over L. This is a multiplication. I apologize for that. Should just say QL. It's not Q dot of L, it's Q times L. Because this is the heat generation of the entire wall, how much heat is being generated by the entire wall, and then how much heat you're losing through flux, through the area of the wall. So that's a times L. It's not an of L. So going ahead and subbing in the values of this, you've got negative 0 plus 10,000, which we calculated earlier, over 0.05, and you end up with 2 times 10 to the 5th watts per meter cubed is equal to Q naught, and that is the how the heat fluxes relate to the heat generation. So that's the value of flux to generation. So they should equal each other, and they actually do. So that's exactly what we wanted to see. The fluxes combine to create the generation, just as we would calculate generation. So that's what that was for.